Voltage from a galvanic cell or cell potential. So we talked about the basic elements you need to put together a galvanic cell. Now we're going to talk about what energy you can expect out of that battery, or as we say for batteries, the voltage or the cell potential, the amount of electrical potential energy. We always have to do this per charge, because if we have a battery, let's say it's like a 9-volt battery, we can't know absolutely how much energy or how much power it's going to have until we know what kind of circuit it's put in. For example, a 9-volt battery that's put into a circuit with a light bulb with a 10 ohm resistance will produce less power than the same 9-volt battery if it's put into a circuit with a 5 ohm resistance a 5 ohm resistance light bulb. So this is more power. Essentially, that's because we'll have less current here, and here we'll have more current, or more electrons flowing around. So this is a little complicated, and we can't say how we're going to hook it up since we're dealing with the battery just on its own. We have to say its potential to create energy. And so instead of saying the total amount of energy it creates, we always discuss the energy per unit charge. Now, back when they made all this stuff up, they didn't know what the size of an electron was, so they didn't make it up for 1 electron. They made it up for 1 coulomb of electrons. But really, that's just like saying the amount of energy for a whole ton of electrons. And it's useful to think about this when you're doing this in your head as just the amount of energy per electron or per an amount of charge. So how can we figure that out for a galvanic cell? Well, what we want to do is we want to compare the strength of the oxidizing agent, the thing that's taking the electrons, that's the thing that's going to give out energy, to the energy of the reducing agent, the thing that's losing its electrons, the thing that's not going to produce energy but is going to cost energy. And to do that, as with all energy measurements, we have to do it relative to some reference point. We can't just do anything. So the reference point that we've chosen here is the reduction of hydrogen. I think you can see that hydrogen is a very common element. And so we've decided to call this amount of reduction energy 0. Now this is a little misleading and I don't want us to get confused here. This shouldn't really be 0. It's just a useful reference point for energy. So again, imagine this sort of sideways scenario here. I don't want to get too distracted by this, but imagine you're in a building. Here's the windows of the building. And you're on the 2nd floor and you drop a ball from this place to this place. The ground out here might make more sense to call height 0, but within the confines of our experiment, that doesn't make a lot of sense. We typically will call the ground floor where we're working 0. In fact, this ground is really relative to some sea level, and so really this maybe should be absolute 0. The bottom line is we have to choose a spot where we're calling the reference, and when we do these measurements, then we can measure them all relative to the reference point. So this energy might be like, 4 volts worth of energy, but we don't know that. All we know is it relative to everybody else, so we got to set somebody to 0, so we're going to set this one to 0. What that means then is that while all of these reductions should be positive energied, we get these negatives down here, and negative doesn't mean that they give away energy when that they lose energy when they get reduced. What it just means is they gain less energy than hydrogen. Okay, so now let's build our battery, and let's build our battery out of something fun. Let's say that we want to have a strong oxidizing agent, so we're going to get a good battery here. And I'm just looking at something that, well, it's expensive and doesn't make a ton of sense, in theory could be used as our battery, and so we're going to reduce gold. So our strong oxidizing agent here is going to be Au3+. We have gold in our solution. We have a golden electrode, and that's going to get reduced. That's going to represent our cathode, and we can see that that has a voltage of 1.4 volts when it gets reduced. Now, let's go down and let's get ourselves a reducing agent. Let's get something like magnesium. Let's go zinc. So zinc is what we're going to have. We want it to be as a reducing agent, so it's got to be on the right-hand side. And our zinc, our negative electrode, is going to change into zinc 2 plus and 2 electrons. And in that process, it's going to get, it would have been negative 0.76 volts going this way. So since we started with this and we're moving to this, we're going to get positive 0.76 volts. Now, I want you to notice something about this. This guy releases energy when he's reduced, but he releases 1.4 volts more than hydrogen would. This guy isn't releasing, this zinc is not releasing energy when it's oxidized here, when it loses its electrons. But what I'm saying is it loses 0.76 volts less energy in this situation than hydrogen would. So if we want to imagine then that all of this is occurring above ground level, and this is where our hydrogen is, and that's where we've called 0, the gold getting oxidized or getting reduced is maybe up here, and the zinc getting reduced is maybe down here. So the total change here in comparison to this is the total of these things. So this one's 0.76 and this one's 1.4, and so my total is 2.16 volts. Now also noticed that I did not bother to do what I usually do, which is balance these half reactions for the number of electrons. In fact, I ignored the number of electrons. Recall then that I said all of these voltages are per unit charge or per individual electron. So when I say that this is producing 2.16 volts, what I mean is 2.16 joules of electricity per coulomb. The number of electrons involved in these reductions and oxidations is already accounted for. So we don't need to balance the number of them. In fact, we neglect the number of them when coming up with this number, because these numbers are already per coulomb, or probably the better way to think of this is per electron. So that's how we can come up with the cell potential. We come up with whatever the oxidation is, and we take this number directly. And then we come up with whatever our reduction is, because we're going backwards. We take the opposite of this number. And then when we do that, we can simply sum them. We neglect the number of electrons because the voltage has already taken into account electrons and is already per electron, so we don't need to adjust for that. I'm going to do a couple more examples when I look at where I'm going to look at given oxidizing agents and reducing agents and how I can come up with their cell potentials using this same chart.